Hi, Dr. Greco. I'm Harrison Williams, and today I'm here to answer the age-old questions. Could German paratroopers in World War II actually jump out of planes without parachutes? And, obviously they can jump out of planes without parachutes, but whether they survive is the problem I'm here to solve today. So clearly, we have to set up the scenario and introduce some parameters into the equation. So the myth was that they could jump out of these planes and land into a amount of snow, and that would soften their impact, and they would supposedly survive. And so the planes would have to fly low enough and slow down enough so that they could do so. The minimum height that one of those German planes could fly is 1,350 meters. And the slowest it could go is 100 miles per hour, which obviously the computer can do some conversions, so we don't have to worry about that right now. This is just to gauge something you've seen before. And then the depth of the snow at that time was about 6 feet. And so obviously we have to get a general idea of what the parachuter was like, his general dimensions. I just used a mass of 85 kilograms, which is about my mass, and a square area. And this is based on a calculation, and so we'll go back to that after I introduce these other constants. So also we have the gravitational constant, which we need to use because on any person who's falling from the sky, they're obviously going to have the force of gravity acting on them at all times, and this is a constant force. And actually, this is technically a non-constant force, but since the change in distance is -1 times the gravitational constant times the mass of the object times the mass of the Earth in this case over the radius of the Earth squared times the unit vector, politically correct, or the exact gravitational equation. And so obviously we need the mass of the Earth, which is constant, 6 times 10 to the 24th kilograms. And the radius of the Earth, obviously, is going to be, in addition to our height at each point, is going to be 6.4 times 10 to the 6th meters. Also, the issue with this problem, given this, since the change of distance is so relatively small, technically we could just use the acceleration of gravity to determine the final velocity once this paratrooper reaches the snow. But the issue is that we actually have a drag force opposing this gravitational force. So the net force is a combination of these two. And the drag force we have is calculated as 1/2 times the density of the fluid, which is causing the drag, times the velocity of the object squared relative to the fluid, times the drag coefficient, times the area of the object that on which drag is being implemented. And obviously, as we're falling from the plane to the top of the snow, this fluid is going to be air. So we need the density of air, which is 1 kilogram per meter cubed. Also, we're going to need the density of snow, because once they reach the snow, that's going to be causing the drag. And so that, as you can see here, is around that time of winter, it's approximately 30% of the density of water. So I use 300 kilograms per meter cubed. And the final thing we need to know is the drag coefficient. Now, the drag coefficient is based upon the properties of the body that is falling through the fluid. So the drag coefficient of a skydiver, after doing some research, is approximately 1.4. So it ranges between 1 and 1.4. Terminal velocity is reached. And so, obviously, this keeps increasing until it matches gravity. Once it matches gravity, the body will, most people can't calculate the average area of their body. So in order to find the area of this paratrooper, I simply set because I wanted to use a constant drag. Drag when it's constant. It's constant when it's equivalent to the gravitational force. So I just use mg equals 1/2 rho v squared times drag coefficient times the area. So I calculated the area to be about, it's approximately 2 mg over rho of air v squared over cd. Now, this v squared is a terminal velocity, 120 miles per hour, which when you do the conversions is about, I believe, 50 meters per second. This rho of air, as I showed, is 1. The drag coefficient is 1.4. The mass is 85 kilograms, and gravity is a constant 9.81. So after calculating this, as you can see, I calculated the average cross-sectional area of a human spread out in the spread eagle position to be approximately 4.5 square feet, or about 1/2 of a square meter. So, like I said, this is a non-constant force because the gravitational force is causing the velocity to be constantly changing. So the problem we have to solve is, how can we calculate this system which acts over a long period of time with a non-constant force? A way to solve this problem is to use computer modeling. I used a Python program, and at a time step of delta t equals 1 times 10 to the negative fifth, I wanted to be as accurate as possible. So I used 1.1, and at every delta t, I use the system of falling to the top of the snow, and then I had to use another loop to calculate falling through the snow, because that's a different drag force, using 8 meters per second. So the question, whether they could survive this impact is based on how much force they can take. Research shows that a human can take approximately 5 Gs of force. A G of force is about 9.81, because that's the gravitational force for 1 kilogram. So whatever we calculate, we just divide that by 9.81, and that's how many Gs of force we have. So how are you going to find the force? Well, we have a velocity. So if we have velocity, we obviously have a mass, and then we can calculate momentum. So this is a start. And so we have, obviously they're hitting the ground. So they're starting with, momentum mv, and they're ending with the momentum of 0, because when they hit the ground, they stop. Technically, they might bounce up, but again, we want to be as lenient as possible, because maybe they don't bounce up. I don't know. And we're just going to use final momentum of 0, just to be, just to give some room. So we have m delta v, change in momentum equals m delta v, which is 85 times the final velocity is 0. This velocity is actually negative 8.8, so we add 8.8 meters per second. So this, this will be the change in momentum. Change in momentum, obviously we're trying to find force, but the change in momentum is equivalent to the impulse, which is also the force times the time over which the force is acted. So the smaller this time, because the impulse is, is set for the system, but the smaller the time, the greater this force will be. The greater the time, obviously, the smaller the force will be. These are just inverse properties. So we have a given change in momentum. What we're going to have to do is determine the time step that we want to use, because we don't want to be too big. We don't want to be too small, because then our force may seem larger than it actually is. I'm going to be extremely lenient, because obviously an input force is 76.3 newtons. Or sorry, the force is I did that wrong. The force is 748.55 newtons, which is 76.3 Gs. As I said before, the human body can only take 5 Gs. 5 as in a lot smaller than that number. So unless they found some, and given we also made some very lenient calculations, obviously a time step much smaller than it should have been. You know, the square area might have been a little bit smaller, making the drag force less. You know, they might have had the plane might not have been able to fly down to its minimum height. You know, the plane might not have been able to slow down to that velocity. We have a lot of factors in the drag coefficient. I use the maximum drag coefficient. So we're lenient on a lot of factors that could actually make this number a lot larger than it is. So unless they found some mechanism to greatly increase the human ability to take an impact, clearly this myth has been busted. Thank you. Again, I'm Harrison Williams, and I approve this message.